So we're going to do sort of work part 2 here. And we're going to look at an example of an inclined plane, which is a simple machine, which is useful for us because it allows us to do things that we couldn't ordinarily do. So we're going to take an object. Let's say we have this object. It's a big box and it weighs 60 kilograms. That's 130 some pounds. It's quite heavy. Heavy enough that it could be hard to lift for several people. Your job, of course, is that you have to lift this up onto the back of a trailer or something because you're moving. You're getting ready for university, you're going off, and you got this 60-pound box of, I don't know, muffins that your mother baked for you. Or perhaps your books and notes, right? But the muffins sound better. And you're going to have to load this up to a height of 2 meters. So let me just put the height in here. 2 meters high. So you got to lift it. Well, if you lift, you recall, hopefully by now you kind of have understood that, if you're lifting something, then you have Fg pulling down and the F applied pushing up. Well, you need to push up with a force that is equal to the gravity or equal to the weight, right? Then we can just, F net really fast is the applied force plus the gravity force. And if we just lifted at constant speed, then F applied would be, this would become minus mg, or 60 times 9.8. And move to the other side, and what is that? 8, 6, 9 to 54, so 58. 588-ish? Is that right? Joule, or force, newtons of applied force. And that's equal to mg. So that's the force you would have to use to lift this up. That's a lot of newtons. Remember, a newton is about the force you would require to lift an apple or hold an apple. The weight of an apple is about a newton. So that's 588 apples you got to lift up all at once. That's a lot. So instead, you use your brains, right? And you say, I'm not going to do that. I'm going to build myself a ramp. So you build a ramp that looks something like this. And of course, this side is up to the 2-meter truck. And you have a box. Now, you're going to push the box all the way up the ramp, but for clarity, I'm just going to draw it sort of in the middle for now. So there's your 60-kilogram box that you're pushing up the ramp. And you built a nice low ramp of 30 degrees because, you build a steep ramp, it's pretty hard. All right. Now, first thing we're going to do is we're going to try to do an ideal situation where we reduce all the friction on the ramp so there's no friction at all. Okay, so once again, we've greased up the ramp. Let's look at a case of no friction. Well, if we look at our free body picture, we have the force of gravity pulling straight down. That doesn't look straight down, does it? That looks like a little bit wacky. So let's see if I can fix that. And let's put this sort of straight down. That's a little better. Fg, force of gravity. Right? And we know what that is. It's 60 times 9.8. And we already figured out from before that it's 588 newtons. Okay, now because we're on a ramp, we're going to do our little trick here, right? Where our motion, our displacement, if I can erase our no friction sign because it's going to be in the way here. Our displacement is the distance up the ramp. So that's our displacement right there. And so that's our x. That's our F net x, right? As usual. So we want to do this. We want to find out how much of the weight, and we know that'll be 30. How much of this weight is along the ramp and how much is perpendicular. Okay. Again, my picture doesn't quite look like it's parallel there, but it's supposed to be. So this would be 588 times the cosine of 30. And down here, 588 times the sine of 30. It doesn't look like a 5, does it? It looks like some kind of Russian letter. Let's put that 5 in better. 588. Okay? And we can figure those out after when we need them. There's no friction. And so again, there is a normal force, right? The normal force would go this way, but I really don't care about the normal force if there's no friction. So why don't we just jump right to our F net x and see what happens? Oh, we should put the applied force on there, right? You're going to have to be pushing up the ramp. Let's use black, I guess. So you're pushing up the ramp this way, and this is F applied. All right. How hard should we push up the ramp? How many newtons should we push with? Well, let's try and push with just enough to move it up the ramp. Okay? So F net x is equal to the F applied up the ramp, and we have the guy over here, which right now I'll just call that FGX in the first statement. And that's it. There's no friction, right? So we want to move at a nice constant speed, so no acceleration, and we can figure out how much force we would need to apply up the ramp. This would be minus 588 sine 30, which is how much? It goes to the other side. Half of that, right? So it'll be 289, I think, or something like that. 294. Yeah, that's better. Let's use your number. 294 newtons is the F applied. Okay, now let's figure out how much work we would have to do. Well, to figure out the work is force times distance times the cosine of the angle. Now, be careful. There is an angle of 30 degrees, but look at our F applied, right here, and look at our displacement. Now, the green arrow up the ramp. They're already lined up. So the F applied x is in line with the displacement. So I really don't need this cos theta any longer. I've kind of already done that. The cos theta has already sort of been taken care of by the fact that I've switched my reference frame so that that's now x. So there is no angle. Technically, theoretically, it's the cosine of 0. 0 angle, which is 1. So it disappears. So what I have to do is figure out how much force I applied. I applied 294 newtons. And how far did I push it? Well, we don't have a number, but look, sine theta, 30 degrees, is equal to 2 over what? Sine theta is a half, so that must be 4. So we used our simple trig to figure out how far it is up the ramp. So that's 4. We multiply 294 times 4. How much is that? 1,176 is the work done. You sure about that? Okay. Well, I believe you. All right. So that's how much work we did. Now, did we figure out how much work we did in the first one? No, we figured out the force here. We applied force, right? Why don't we just compare the two? Let's go back and let's figure out the work we did there. That one was force times distance, and it was 588 multiplied by the distance, but here we were lifting only 2 meters up, straight up. So it's times 2. How much is that? How come that is exactly the same as using the ramp, the amount of work I did? Look at the work over here. There it is. Why bother with the ramp if it's the same amount of work? Kind of makes it seem pointless, doesn't it? But that's not what ramps are for. Of course we did the same work. We ended up with a box 2 meters higher than when we started. But what was different was, and here's the reason for using the ramp, in the first case, the applied force that we had to use was 588 newtons of force. Whereas the applied force that we are using with the ramp is only 294 newtons. And so what the ramp did is we got away with it. The force lifting was, what was it, 588. The force on the ramp is 294 newtons. It's a lot less force. But we managed to do the same amount of work. So it seems like we got a deal here. But we didn't really get a deal because we also, this was a 2-meter lift, this was a 4-meter push. So what the ramp has done is it's a trade-off. It allows us to use less force, but the trade-off or the payment for that is you have to push for a longer distance. Trade-off between force and distance. And that's because mathematically, remember, if work equals force times distance, here's some work, and here's a force, and here's a distance. Well, I can get the same amount of work done if I use a very tiny force, but to compensate, I use a much bigger distance. It would still give me the same amount, right? And I can get the same amount of work done if I use a very large force in a very tiny distance. Well, this is the one that humans like because humans suck at applying force. We are not very strong. We would rather apply small forces over large distances to get the same amount of work done than applying very large forces over small distances. And that's what the ramp does. It's a trade-off between force and distance. It's a simple machine. We call the inclined plane a simple machine. All right? Now, guess what we're going to do? We're going to add friction to the same picture. And let's see if we can do that and see how everything changes. So let's go quickly through this part, because we've done most of this work already. 30-degree ramp. 60-kilogram box. Let's add a frictional coefficient of mu. I'll put it down here. Mu is going to be 0.2, let's just say. Okay. All right, so let's start. Fg, gravity. Normal force, Fn. Applied force, up here. Okay, and now, I'll add it in blue so we don't forget about it. Friction. Whoa, what happened there? That's the wrong button. We don't want that. Blue, frictional force going this way. So we have the friction added in. But we know how to handle this. We still resolve our gravity into the two components. And we have the numbers. We've already done it. So if you recall, I think this was 588, right? mg. This was 30 degrees in here. So it's 588. This was 294, I believe. Sine 30. And this one was how much? What was the other? Was it 4? You guys don't remember? I'll have to go look. Right here. Well, we never actually figured it out, did we? Because we didn't need it. How much is it? 509.2. Excellent. So we put that. We now we need it, right? Because of the nasty friction. 509.2. Okay, so we jump into our F net Y equation, and we figure out the normal force. We have to do this step now because we have an FGY, right? And we have an FN pushing up. We want zero acceleration in the Y direction, and we want 509.2 is down. So the FN is 509.2 up. Good. Then we jump over to our F net X equation to see what would happen and describe the situation. FGX and F applied X. Actually, F applied is already X. It's already on there, so we don't need an X. And also a frictional force now. Again, we're going to try to push this at a constant speed. So we're going to have 0 equals 294 to the sort of leftish, an applied force to the right that we're trying to figure out, and a frictional force working against us of 0.2 mu times Fn 509.2. Whoops, too many decimals in there. 509.2. Okay, so we crunch our numbers, and so if I move all those numbers to the other side, it's 294, and it's going to be adding 418 So is that 18.4, I think? No, 101, sorry, 0.84, right? Gotta get the, double check on the calculator as we zip through this. So what's the final answer for the F applied?
395.
Did we make any mistakes? No? Good. F applied. Compare that to the lifting force, which I recall was the weight, 588. And it was 294 in the second example without friction. So this actually means I got to push a little harder now, don't I? Because of the friction. Let's figure out the work. The work I would do is equal to force times distance. And in this particular case, the cos theta is already lined up. I don't really need cos theta because the force I'm applying is in the same line as the displacement. So it's cos theta is like a 1. So I'm applying 395.8 newtons of force, and I'm still pushing up the ramp at 4. So when you multiply that, 4 8s are 32, 5s are 23, 4 9s are 36, and 2 is 8, 4 3s are 12. Is that 14, 8 3? Is that right? 15? Oops. I haven't had lunch yet, that's why. My brain is losing its sugar. 1583.2-ish. That's the joules of work done. Now look at here. I've actually done more work than lifting. I'll go right back to the start. I can probably do that this way faster. Here it was. 1176 was the joules of work lifting. And now I'm actually doing way more work. But I'm still going to use the ramp because the point of the ramp is look at the force I'm applying. I'm still using less force than lifting. So sometimes we use simple machines that have friction that work against us, and we actually do more work than necessary so we can use less force. Now here's the question I would like you to think about. A little bit of friction means that I had to apply more force. What if there was a little bit more friction? Well, this force would go up a little bit more, wouldn't it? And a little more friction, a little more force. At some point, we would hit a point where the ramp kind of became useless. What would make a ramp useless? Remember what I'm trying to do. I'm trying to make it easier for me to lift. Well, if it was 588 to lift it straight up, if the friction makes this applied force go up to 588 or higher, I might as well just lift it because I'm not gaining any force advantage, am I? So when the force applied up the ramp, because of the increasing friction, is equal to the force of gravity, well, then I just lift it straight up into the truck. Doesn't make sense to push it up a ramp and use more force than I would if I was lifting. So my question to you is, what coefficient of friction makes the ramp useless? I'd like you to figure that out on your own as a little exercise. Not useful, useless. Useless. In other words, it's not saving me any force. So what coefficient of friction makes the ramp useless? That's what I'm going to leave with you just to entertain you in your off hours.